expect everybody to find a place here, and we'll start. So it's my honor to introduce Rebecca today. Rebecca has had a long association with the Giant Magellan Telescope beginning over a decade ago, and only late last year she rejoined Carnegie Observatories as a staff member and rejoined the project as the project scientist. Rebecca's research interests include the diffuse light in galaxy clusters and the formation history of globular clusters in nearby galaxies. Her curiosity, I guess beginning as a graduate student, about the instruments that she used for these observations led to another one of her specialties, which is optics and instruments. After receiving her PhD in 1998 from Caltech, she became a Hubble Fellow at Carnegie Observatories, where she worked with Steve Schechtman. In what seemed like a puff of smoke, she absorbed a deep knowledge of optics and instruments and went on to lead the design with Steve Schechtman of the development of the Mike spectrograph, which is familiar to high dispersion spectroscopists here. In the years that followed, Rebecca became one of the foremost designers of astronomical optics and instruments. Following her postdoc, Rebecca joined the faculty at the University of Michigan, and she became a member of the small group of scientists and engineers that developed the GMT conceptual design. In 2007, she left Michigan to join the faculty at the University of California, Santa Cruz, where she was professor and PI of a major instrument for the other U.S. ELT project, the 30-meter telescope. So you can imagine that the birds sweetly sang when Rebecca rejoined the GMT community last year. Welcome to the CFA.
Thank you very much. I am very happy to be here and very happy to be back in the GMT partnership. Let's see if I can get this displaying. All right. So I'm going to give you an overview today of the GMT project. I can just touch quickly on the topics I'm going to cover in this. First, I'm going to just give you a technical overview of the telescope, give you a little bit of an idea of what the project status is, and then discuss the GMT science case, which should probably be familiar to most of you, as it's the sorts of things that I hope that you would think to do with a next generation telescope, ground-based telescopes. But I want to focus on, for a few of the examples in the GMT science case, really focus on the unique strengths of GMT, and particularly on some simulations that can really show you what the advancements will be in the sorts of data that can be collected with GMT as opposed to what's being collected now. So we'll try to concentrate on that, and then finally give you an overview of the first generation instruments. And if we get through all of that, we'll be in good shape. So if I skip over anything, that will be your cue to ask me about it later, during the question session, so that we can make up a little time. Okay, so is it possible to move this podium back just a tiny bit, or does it? Whoop, excellent. All right. Sorry. Okay, so this gives you a quick idea of where the partner institutions are located. Of course, the U.S. institutions we're mostly familiar with. There's also a Korean Astronomical Sciences Institution in Korea, and we've got our astronomical partners. For those of you who haven't been there, and shame on you if this is you, that's where Las Campañas Observatory is located in Chile. And we are eagerly anticipating the arrival of potentially some new partners, including Sao Paulo, which I'll talk about in just a minute. Oops, weren't going to show that. All right, so the partner institutions are listed here. This is as of 2014. I actually had to think about adding a new map to my talk because the old map didn't show where some of the new partners may be located, so that's a little foreshadowing for the next time I give this talk. So the partners are listed here. Right now, each either holds or is intending to hold between 5 and 10% share, and about 85% of the partnership is spoken for at present. And as I just mentioned, the discussions are underway for more potential partners, and we hope to be hearing some answers on those soon. So let me get straight to covering some of the technical details of the telescope. You can see this is a quick top view, or somewhat top view of the telescope with its mirror covers back. So the telescope is from side to side, 25.4 meters in diameter. It will, of course, do optical and IR observations. And it will have up to 7 instruments mounted simultaneously, which we'll get back to that in a minute. And you can just get a general picture of or general understanding of the structure of the telescope here. You see the 7 segments. The secondary is there. I can show you you get a little bit better idea of the optical path from this one. So the primary segments are 8.4 meters in diameter. That's about the largest practical rigid segment, and those mirrors are made at the Stewart Observatory Mirror Lab, of course. Each of the primary segments are conjugate to a single segment of the secondary mirror. So the fine alignment can actually be controlled with the secondary mirror, and you don't. And that allows you to simplify some of the control and focus of the telescope. One of the advantages of this telescope, and there are a variety of it, I'm always asked, particularly since I have been involved in both projects and have an internal view of both projects, I frequently am asked to compare the two projects. And so I have just gone ahead and built into my talk some of the comparisons that I think are relevant and are particularly critical to the performance of the telescope. So I'll just be bringing those up as we go along. But one of the things that I think is very important is that this telescope has only 2 optical prescriptions. These outer off-axis segments are a particular shape. The inner segment is symmetric. But that's only 2 optical prescriptions for the primary mirror. The ELT and EELT and TMT have 84 and 140 prescriptions, because the curvature has to change as you go out in radius from the primary mirror. And that's important because it's very difficult to imagine getting all of those exactly right. So this makes it a little bit easier to have a telescope that's going to make good images. Also, large circuits enable higher contrast AO, and since one of the primary selling points of this next generation of telescopes is their adaptive optics capabilities, and high contrast AO being the most aggressive form, it's important to realize that you get better adaptive optics correction and higher contrast when there aren't gaps in between segments. So we've got 1, 2, 3, 4, 5, 6 segments that are going to have absolutely no obscuration in their optical path, which is absolutely unique for an optical telescope on the ground. Also, the gaps in between can be easily masked out at the pupil in an infrared instrument, which is not something that will be possible for either the ELT or TMT because of the vast number of gaps that you have in those primaries. Okay, the next important thing about this telescope is that it's an aplanatic Gregorian design. I'll come back to that in a minute, but without getting into the technical details, it allows this design to have a very wide field of view, unheard of for one of the ELTs. 10 arc minutes uncorrected and 20 arc minutes with a wide field corrector. Also, it means that because it's a Gregorian, and I'll show an optical design later that lets you see this, there's actually the primary mirror forms an image, a real image, in front of the secondary mirror, which is very useful for calibrating, for alignment, for calibration, for flat fielding. It's a very handy thing. Second, the next thing I was going to point out is that the secondary position in a Gregorian telescope actually enables ground layer correction, because the secondary mirror is conjugate to a layer above most of the ground layer turbulence, which allows for ground layer adaptive optics correction, which with only 2 bounces, unlike with the light only hitting the primary and the secondary mirror instead of many optics downstream, which again is very advantageous for adaptive optics. Finally, because of the fast focal ratio of this telescope, it's a very compact structure. And because the ELT and TMT also have very fast primary mirrors, but they have very much longer final focal ratios. And I think this is very important because the fast focal ratio of the telescope overall makes for a smaller plate scale, which makes the instruments infinitely more designable and fabricable, which, I mean, the telescopes are light buckets. The things that actually do the science are the instruments. So if you can't build the instruments, the telescope is of dubious utility. So making a plate scale that you can actually use, I think, is a big advantage of this telescope. And having designed one of the first light wide field optical instruments for TMT, I can say that it's a gigantic advantage in instrument design. All right, you get a little bit better view of the telescope structure here. What you're looking at is from the ground level up. This is showing the pier on which the telescope sits, the azimuth track on which the telescope rotates, the observing floor, and the azimuth structure that allow the telescope to spin. The elevation axis is here. That's the line about which the telescope nods to come from zenith to horizon. And you can see what's labeled here is the OSS. That's the optical support structure. And I'm going to talk about this braced hexapod in just a minute. You can see the secondary up there. So this is one thing that's very interesting about this structure is how compact it is. The C-rings are actually underneath on all of the last generation of telescopes, almost all of the last generation of telescopes. The C-rings were outside of the primary mirror, which allowed for there to be Naismith platforms, but also made the telescope structure a lot less compact. This allows for much more rigidity. The moving mass is actually fairly small for a telescope this size. I'm going to come back to that, and the fixed mass and total steel numbers are listed there just for completeness. I want to point out exactly how stiff this structure is, and stiffness is extremely important for the performance of the telescope. So the first resonant frequency is around 5 hertz, but there's very little motion there. So the first one that actually impacts images is up around 10 hertz. That is in contrast, again, to the ELT and TMT, which have much, much lower resonant frequencies, which means that it will be much easier to excite those frequencies with wind buffet, with pressure from the wind, which will mean that they will almost always have to be really actively controlling those vibrations and their optics. Okay, so I was just going to give you some numbers for comparison here to emphasize exactly how low mass this structure is. It's compared to Palomar, there is a tenth the mass in the structure compared to the mass area ratio. And for Magellan, it's actually almost the same, which is very surprising considering that this is 3 times the size of Magellan. So we're doing a good job in trying to keep these structures, or this structure, beneficial for fabrication and performance. Okay, so most of you aren't going to get to Arizona to see the mirrors being made there, so I thought I'd show you what they look like in the mirror lab and show you a video of the fabrication of the mirrors. But first, these are, again, the largest mirrors available, 8.4 meters. They are very good for fast thermal equilibration, which is critical for image quality. They're very stiff. There is an established production line, and in fact, we already have the first off-axis segment completely made. The GMT off-axis segments are highly aspheric, so these were very difficult to develop the methodology to not only polish the mirrors, but actually test the surfaces. So it's very good news that we have the first one of these made, and that risk has been completely retired then. And finally, we have, certainly within the partnership, an enormous amount of experience controlling these mirrors. So they have proven support and ventilation systems with which we have an enormous amount of experience. So again, this is I think this is a very of significant strength for the partnership, whereas getting the primary mirror segments made for either ELT or TMT is a totally starting from scratch problem. All right, so the primary mirror segments, the first one, as I already said, is complete. You can see that we've got 4 more in process. One is in the currently having the rear surface polished. One was cast last August and is now cooling. We're getting the glass purchased for the glass has been purchased for the 4th, and casting is planned for next January. And we're in the process of purchasing the glass for the 5th. The 4th mirror segment will actually be the center segment. The reason we're breaking the sequence of making all the edge segments first is explicitly so that we can come online early with 4 mirrors as rapidly as possible, and that center segment is important for the phasing and the alignment of the primary. Okay, so I was going to show you a video next showing the mirrors being made. It's about a 3-minute video, so I think we'll come back to it. So if you're particularly interested, just let me know during the questions. But what this is showing you is the glass placed in the mold, ready to be melted and spun into the approximate shape that the final mirror will take. So the glass has to be placed in there. You see a bridge out here for the glass to be placed in because the honeycomb structure that the glass melts into is fragile and you can't just chuck the glass in. So that's the process. We'll come back to the video. So again, Las Campanas Observatory in Chile. This is the west coast of the United States. You can see Los Angeles and Baja Peninsula down here to give you a little bit of the scale. This, by comparison, is what the southern tip of South America looks like, and you can see how dark Las Campanas Observatory is, which is, of course, why we are building more telescopes there, and part of the reason why Las Campanas is such a good site. This is the other reason why Las Campanas is such a good site. That is what the sky looks like 365 days a year. That is typical for Las Campanas. What's less typical is the herd of guanacos that are seen there looking up at the Magellan Dome. But no, seriously, Las Campanas is truly photometric for a shockingly large fraction of the time and has very good natural seeing. It also has an established infrastructure. So as you all know, we own the site. This is not a small deal. It is difficult to get permission and permitting to build the telescope. So that is something we don't have to mess with. There's access roads, water, although not all the boroughs find the water. There's power, there are communications networks, maintenance shops, lodging, there's headquarters in La Serena. This is a gigantic advantage in getting the next generation telescope started. What you see here is the peak where Magellan is and the 100-inch, and you can see where the support dome. Oh, I believe no, that's not it. I think that's where the support hotel and lodge are. But the civil work, so over here is Las Campanas Observatory. This is before the site was leveled. It has already, the top has already been taken off of that peak. And the civil work, concrete work, is going to start later in this year. That is, if, of course, we get construction approval, which we are anticipating. So I have a video that shows that summit support also, which we can come back to at the end if we have time. But you can see the leveled peak. The telescope in what is the baseline dome design. This dome, the enclosure design, has actually evolved a little bit in a very positive way. And this is the summit support building where we'll do illuminize the mirrors and have the facilities to support instrument assembly and secondary assembly and servicing. All right, so let's take a look at what the optical path looks like for this telescope. So you can see the light coming from the sky over here. So sometimes people don't think about it this way, but it's helpful to stop for a minute and just think. Light coming from the sky is from objects at infinity are always coming parallel. So light coming from one object is coming parallel from this direction. Light coming from another object is It's coming parallel, just off axis, right? So this is light coming from a single source is what's shown here, so it's coming to a single focus. Okay, so light coming from infinity hits the primary mirror, goes up to the secondary, and back down to one of 3 instrument ports, which is how we can have 7 instruments mounted and hot to use simultaneously on any given, or in rapid succession on any given night for target of opportunity sorts of science. Another important point here, before I move on to describing what the instrument ports are, is that the light path only hits 2 mirrors, even with adaptive optics, before it gets to an instrument. So there are lots of ways to lose light in an instrument, or in a telescope. And I like to point out this because, you know, occasionally we get attacked, for lack of a better word, for having a 25-meter telescope as opposed to a 30-meter telescope. But one way to make that difference up very, very quickly is by, or rather, one way to lose that advantage very, very quickly is by having 6 bounces or 10 bounces before you get to your instruments. So at each of those bounces, you lose something between about 10 and 20% of the light, typically. So having only 2 bounces does essentially make this essentially a larger telescope for direct comparison with the others. So that's a very important point. Another thing is not keeping your mirrors illuminated, well illuminized and cleaned is an easy way to lose light. We'll come back to that later. But the configurations shown here are, the first one is the direct Gregorian narrow field focus. That gives you a 10 arc minute field of view, and that's the location for wide field spectrograph without a corrector. The direct Gregorian focus with a wide field corrector is shown here, and that would give you a 20 arc minute field of view that could be fully accessed with fibers. That's the current plan. At some point in the future, we may have a direct slit-fed wide field optical spectrograph over that full field of view, but it's not the plan now. And then you can see a folded port instrument platform shown there, which has a 3 arc minute field of view, and that's the location for high resolution spectrographs or adaptive optics instruments. There is yet another stable port where G-clef will be located, and I'll show that in a minute. In fact, here it is. So we've got the main instrument platform is shown here, and what we call the gravity invariant station, where instruments that are particularly need particular stability will be located. The direct Gregorian instruments are located down here underneath the primary mirror. So remember I said the C-rings it's a very compact structure, and the C-rings are actually under the primary mirror. That means you don't have Naismith ports. So instead of Naismith ports, what we have is a direct feed down below the primary mirror to direct Gregorian instrument location. And finally, you can see the folded port location is here. So I want to point out again about the direct Gregorian port, that it should have better performance and lower cost. Better performance because it is in a more stable location. There should be lower vibrations, less flopping around than you have for platforms that are located outside of the primary structure. Okay, so going through these very quickly. So this lists the instruments that were considered for conceptual designs. We've decided to move ahead with 2 of these, the visible high-resolution spectrograph, which Andy here is the PI, and GMAX, which is being PI'd at Texas A&M. These are the instruments that are being planned for stage 1 first light. The instruments that are being planned for later stages with the adaptive optics are also listed here. We've got an infrared imager and IFU called GMTIFs, and an infrared high-resolution spectrograph called GMT NIRS. There are others listed here that, just these 2, which have capabilities that are being deferred. They're not planned for the first generation of instruments at this point, but they are capabilities that we very much are interested in and will certainly be considered for later stages. And finally, manifest is listed here. So the preliminary design studies are underway for the instruments that are listed at the bottom. Okay, so another one of the real advantages of this telescope that I want to point out is the secondary truss system. This is an extremely unusual looking truss that you probably certainly does not look like anything you've seen before, but it has a number of substantial advantages. So we call this a braced hexapod. So a hexapod, has 6 legs, and you might imagine a more standard hexapod or distribution would have the legs coming out like this, but they're crossed at a point halfway up so that they do not obscure the light to the outer segments of the primary mirror at all. So this is extremely good for adaptive optics, as I've already mentioned. And if I show you the light path to any of those primary mirrors, you can, the outer segments of the primary, you can see that they have absolutely nothing in the way. If you were after the highest contrast adaptive optics, undoubtedly what you would do is ignore the inner segment entirely and simply concentrate on the completely pristine image on those outer segments. And that is, again, a configuration that is not repeated on any ground-based telescope anywhere. So for adaptive optics, this should be spectacular. So the hexapod legs are crossed and braced, which should make them very stiff, lightweight. There's very low wind area. Again, it blocks very little light. That's certainly useful for optical as well as AO use. And even more importantly, it allows us to swap out these outer segments for maintenance and reilluminizing the mirror. So the outer segments can come out without the support structure for the secondary interfering at all, and they come out actually in this direction as opposed to radially to avoid the secondary struts. So I've already mentioned the adaptive optics advantage of a Gregorian. Let me be a little bit more clear about what that is. A Ritchey-Chrétien telescope looks like the following. So we've got blue, black, and red light coming parallel from 3 different objects in the sky and coming to a focus then at 3 different locations in the focal plane. But what you can see from looking at the light as it comes to the primary mirror and then up to the secondary is that here's the secondary in an RC telescope. The image formed by the primary mirror alone is imaginary. So the light never gets to this point. It's interrupted by the secondary and is focused back down. On a Gregorian, that doesn't happen. On a Gregorian, you actually form the image from the primary mirror in front of the secondary, which is very useful for calibrating an adaptive optics system. So this is, again, a significant advantage for AO. But even more, the secondary mirror is conjugate, as I've already mentioned, to a point above the ground layer, which allows you to do ground layer adaptive optics, again, with just 2 bounces to the instrument. The other telescopes will have ground layer adaptive optics as well, but with more like 6 or 10 bounces to the instrument. Okay, so just to be crystal clear about what is adaptive optics. So the light coming through the atmosphere to the telescope gets distorted by the thermal variations and density variations in the atmosphere, which cause index variations. And so the wavefront goes from being a nice, pristine, perfectly flat wavefront to having the structure, some structure, as illustrated here. And somewhere along the optical path, what happens in an adaptive optics system is you split that off. You split the beam so that some of the light is going to the instrument, some of it's going to a wavefront sensor. That wavefront sensor measures what that distorted wavefront is and then changes some mirror along the optical path to essentially perfectly compensate for the structure in that wavefront, so that once the system is operating in closed loop, then the light coming to the instrument sees a perfectly corrected wavefront. So in Magellan, where we do the correction is with adaptive secondary mirrors. So people here at at an institution where adaptive secondaries are well known might understand this, but this is a useful thing to explain at some of the partners where this is not seen. So I can just go over this to make sure everybody is on the same page. So these adaptive secondaries are built on and are being designed by vendors that have played a role in all of these existing adaptive secondary systems. And so between the partnership itself and the vendors, there's an enormous amount of experience with these systems. The wavefront sensors that are going to be used will actually depend on which instruments are being used and which ports those instruments are located at. So there'll be, for ground layer AO, there will be one set of wavefront sensors and guiders. For natural, we'll have implementation of natural guide star adaptive optics and also laser tomography adaptive optics. So let's see. So we intend to come online with a set of mirrors that are not adaptive, with what we call fast steering secondary mirrors. These are stiff mirrors that are adjusted for tip tilt and and piston that can also be used to correct for the alignment of the primaries. And these assemblies should be completely interchangeable so that we can service the adaptive secondaries and eventually swap in the adaptive secondaries when they are ready for use. All of the mirrors are a little over 1 meter in diameter, and as I already mentioned, there are 6 degrees of freedom, tip, tilt, and piston in both designs, and again conjugate to the ground layer. This is what the adaptive secondary face sheet looks like. This is hanging in the Magellan coating tank obviously at Magellan. So these are pretty amazing structures. This is 2 millimeters thick. It's a zero-dur face sheet that is reilluminized and has magnetic. Has permanent magnets glued to the back of the face sheet for actuation. And I don't want to go into all the details here. I just want to give you a sense of how complex and these secondaries are. So you can see the one for the VLT, which is made by the same vendors, Microgate and ADS, that are making the GMT secondaries and the other secondaries I've already mentioned. And you can see this is the current state of the art. I believe that the density of actuators for the GMT mirrors are slightly lower density than this. Just to give you a visceral sense of what adaptive optics can do now and where adaptive optics is going next, this shows detection with a coronagraph of planets, of several planets in one system. This is with, you can see the scale in the corner, so I think that's a fairly spectacular illustration of what can be done currently. I'm going to come back to this example in a minute. This shows, oops, I wanted to show, let you see the another illustration of what's been done with the Palomar Observatory adaptive optics. So again, this is what's possible now. And finally, this is an image of the center of our galaxy from Keck and the UCLA Galactic Center Group. So if this is what can be done now, where are we headed? With GMT, we should, at 1.6 microns, be able to achieve 0.03 arcsecond resolution as opposed to the 0.4 arcsecond native resolution at that wavelength. So that's 30 times higher spatial resolution at the diffraction limit, but it would allow for 40 times higher point source sensitivity, so getting that much more light into the core. And if you're in a crowded region and you're able to reject then light from nearby sources, it allows for about 100 times higher contrast near bright stars. So this is what natural seeing looks like. That's 0.6 arcseconds. This is what you can get with HST and NICMOS. This is what is predicted with JWST and NIRCam. And this is a simulation of what you would expect to get with GMT. I wasn't supposed to make you laugh. I hope that you're just laughing because you're so happy. But yes, so that is the goal of building these next generation of telescopes. And again, I told you I wanted to emphasize simulations and examples of what we expect to see with GMT. This is a picture of the Hubble Deep Field. And that is taking one galaxy and illustrating what we expect to be able to get with this galaxy that's in the center here, what you expect to be able to get with GMT adaptive optics. All right, so let me move into the part of the talk where I give you a little bit of the status of the project. So the last year, 2013, was an unbelievable sprint, marathon, I don't even know what to call it, of PDRs. So it was the end of our design development phase, and design phases always usually end with reviews. So we had 5 independent reviews with international review panels, and the subsystems that were reviewed were the enclosure and facilities, the adaptive optics system, the telescope system itself. We had a system level PDR just in January of this year, and one weekend after the system level PDR came to a conclusion, we had the cost and management review for the project, which was particularly punishing. The only thing that's left to be reviewed is the software and controls, which really require some understanding of the subsystem first, so I think that's a fairly logical sequence for these things to come in, and that is planned for the coming fall. The common theme from all of the review panels was that all of these subsystems were ready to go into the next phase, and in fact we even got a direct quote from the system level PDR was that we should in fact move forward to construction as quickly as possible. So that message was carried to the board, and we are looking forward to getting a positive a thumbs up to move into construction just in the next few months, hopefully. But the next steps are to start placing the contracts, identify our vendors, and get some of these designs completed to the point where we can go to fabrication. So there's a ramp up coming, and we are looking forward to that and in the process of doing that. Okay, so I don't see a clock. Oh, all right. So scientific, okay. Scientific motivation, I've already had discussions with some of you that if we tried to write down exactly what we intend to do with this telescope today, it would seem very antiquated by the time we have the telescope commissioned. So the scientific case for the telescope really focuses on sort of 3 legs. One is discovery space, where we really want to think about just new capabilities and broad areas for discovery. And the broad areas for discovery really come from the greater sensitivity that not only comes with the increase in the collecting area of the primary, but the dramatically larger increase in sensitivity that comes with adaptive optics, and also the increase in angular resolution. So in general, just the discovery space that's allowed by that larger primary mirror is huge. We also can write down, of course, a number of contemporary science goals, and these focus on both the interests of the partnership and things that are recognized by the community in general as being the most interesting problems for the next decade and the coming decades. And so those are listed here. Formation and properties of extrasolar planets, stellar populations, chemical evolution, galaxy assembly and evolution, black hole growth, dark matter, dark energy, fundamental physics, first light, and transient phenomena. And of course, the last leg of the science case is really synergy with the other observatories that we expect to be coming online and to be in operation during the lifetime of GMT, and those include the observatories listed here, which are all complementary. So the point is to try to think about the different priorities and capabilities of these other observatories, and in planning GMT and the instrument suite for GMT, try to maximize the impact that GMT will have by its complementarity with these. So very quickly we can go through some of the key science cases, and again I'm going to focus on some of these that really show exactly how much more we can expect to get with GMT. So in the case of exoplanet science, some of the questions are, how do planetary systems form and evolve? And is there evidence in the chemistry of exoplanet atmospheres that they can support life? So the point here is that I think we've gotten beyond the point of well beyond the point of just identifying planets, and we want to try to get enough of a sample of planets at all different sorts of separations that we can try to understand how they have evolved and how they have come to exist in their current configuration. So direct imaging is very useful for the largest star-planet separations. Radial velocity detections are useful for smaller star-planet separations, and very importantly, they provide masses for the planets. And finally, transient observations provide direct measurements of the sizes of the planets, and when combined with radial velocity detections can actually be used to get densities, and that can tell you a lot about the structure of the planet. In addition, transient observations can provide the atmospheric chemistry, which is a very exciting development. So this is the example I was showing you earlier in blue. Actually, this is direct exoplanet imaging. Reflected light studies are very difficult at shorter wavelengths in the near IR. Require very high contrast, have very small inner working angles, and therefore require a suppression of the diffraction with phase apodization, coronography. So there's a handful of good systems today. It's a lot easier to do these sorts of studies in emitted light because the contrasts that are required are a little bit more modest and the inner working angles are a little larger. So I want to show you an example of what we expect to do with GMT. This is showing sort of the state of the art today. This is showing, so this is the same, this is showing the beta PIC exoplanet system, where the separation is the distance is 20 parsecs to the system, and the separation I don't remember, but this is about a 10 Jupiter mass exoplanet. This was taken with the VLT system. This is what we expect to be able to get with this, observing the same system with GMT. So this is not only the 10 Jupiter mass planet that's detected, but included in this simulation are some smaller planets at a variety of distances to illustrate exactly how much fainter you would be able to go with GMT. So this is assuming that the observations are at 3.5 microns, 90% Strel ratio, again adaptive phase imaging, and about a 1-hour integration with multiple images co-added. This is an illustration of, this is showing the current state of the art for radial velocity detections. And of course, what you're measuring here is the motion of the star due to the orbit of the planet around it. So you're not measuring directly the light from the planet, but measuring the motion of the star. So the current state of the art is around 1 meter per second. The more typical precisions are around 3 to 4. It requires very high stability, very high cadence observations. You have to revisit these stars a very large number of times, partly to beat down the noise, partly to just get good enough coverage throughout the orbital phase. And it requires very high resolution and very high signal to noise, lots of photons, bright stars. So I want to particularly draw your attention to the scale that's shown here. This is in meters per second. What we expect to be able to do with GMT is shown here in centimeters per second. This will allow us to go to fainter stars and lower mass planets and get down to 1 to 2 Earth mass planets in the habitable zone of G-type stars. So this is what GCLEF is going to do. Andy looks up. All right. So this is something that Andy doesn't have to worry about, so we'll talk about this next. So this is getting into the question of, is there evidence in the chemistry of exoplanet atmospheres that they can support life. And of course, the way we can start to address this question is by looking at the starlight as it transits through the atmosphere of a planet when that planet is directly transiting in front of the star. And this is showing a comparison of simulations with observations from VLT and the FORS instrument. And you can see that several models can be ruled out from these data to understand the composition of that atmosphere. This is showing more of the same, which I think in the interest of time I'll skip over. So let me get on to the topic of galaxy formation and evolution. So some of the key science questions here are the history and chemical enrichment of galaxies, and low mass dwarf galaxies are particularly useful laboratories for addressing this question. And then also how galaxies are assembled, thinking about whether mergers or gas conversion dominate in the growth of galaxies, and how early type galaxies in particular grow. And I've listed a number of other questions from the GMT science book here in gray, and in the previous pages in gray. And the science book is available on the web, and all of these cases and all these simulations are actually present in that science book if you're interested. So the first question I just mentioned was getting at the chemical evolution of galaxies, and we can rephrase that slightly as, are ultra low mass galaxies closed box systems, or are they clearing gas and metals during their bursts of star formation? And the approach to trying to understand, to make progress on this today, focuses on measuring the abundances and the abundance patterns of individual stars in low-mass dwarf galaxies in the local group. So you can see color magnitude diagrams, so magnitude versus color for 8 dwarf galaxies in the local group. And the first thing that you can see here, well, first the current detection limits for the spectroscopy that is required to measure abundances is shown here in red. So the first thing you can see is that there are not very many stars accessible in very many of these dwarf galaxies. And the point here is that in order to try to understand the chemical evolution of a galaxy, you have to target old stars. You can't just target the brightest, youngest stars. They would tell you about the current abundance of the current gas phase abundance in the galaxy, which is not helpful for history. So the problem is that old stars are faint, and particularly at large distances, they are even fainter. So that means it is simply hard to get a very good sample of old stars in these galaxies. Also, low-mass dwarfs don't contain many stars. So the number of targets available is even smaller. So the point is that with the detection limits of GMT, it just completely opens up this problem with a whole new accessible sample of stars. So the next point we brought up was, are star-forming galaxies that we see at high redshift rotating disks or dynamically hot merging systems? Again, this is getting at the question of how the formation of and growth of galaxies progresses. So looking here at what we call velocity channel maps, this is taken with IFU spectroscopy. So what you're seeing here is a bunch of different velocity channels, or relative to the central velocity of the galaxy. So here's gas moving at minus 20 kilometers per second and at plus 400 kilometers per second relative to the central speed of the galaxy. And this is data taken with the VLT and the Symphony instrument with adaptive optics. And down here, so this is with adaptive optics, this is without, but in both cases you can see rotation of the galaxy that shows coherence, not just assembly by merging systems, so that it looks more like a coherent rotating system rather than a dynamically hot system. But the point is that the targets that you can access currently, and this is again the state of the art, are about 5 L star, 5 times the brightness of the Milky Way. So these are not typical galaxies. at these redshifts. And what you would hope to do is get to much lower mass galaxies and possibly even to higher redshifts. But this is showing, again, a simulation of what we would expect to get with GMT. I'm starting with a comparison of what you would be able to see with the current IFU system on Gemini. So this is a simulation that's starting from a galaxy in the Hubble Ultra Deep Field. So this would be the integrated light that you would see from Gemini in all one channel now. And this shows it split up into different channel maps. So you can see that the signal noise is very low, and it would be very hard to make a clear detection of what you're seeing there. This is what you would expect to be able to get in the same integration time and at a much lower mass galaxy with GMT. So this would allow us to target more Milky Way mass galaxies at high redshift. And the last, second to last topic I want to bring up is first light reionization. So the questions here are, when was the universe reionized, and what fraction of ionizing radiation escapes from young galaxies? So the point here is to try to understand this critical region where the universe went from being essentially all neutral and not allowing the free streaming of the photons that we would see from star-forming regions to the universe that we see around us today, which is essentially entirely ionized. So in order to address the question of when did the universe become reionized, the approach is to search essentially for Lyman alpha emission from high redshift galaxies. And the point is that Lyman alpha emission is very sensitive to the fraction of reionization. And from the current state of affairs is that it seems to be that the distribution of Lyman alpha equivalent widths, the equivalent width of Lyman alpha emission from detectable sources, is very high in the range 4 to 6, but it falls off rapidly right around a redshift of 7, which of course suggests that that is about the redshift at which reionization was taking place. But it's there are a variety of what you'd really like to do is get a complete enough sample to get some sense of whether this was happening in a very spotty way, exactly what redshift this was happening at, how much, what those objects that are causing reionization really look like. And this shows, again, state-of-the-art. This is observation with the new Mossfire instrument on Keck, where they surveyed 40 candidates and only found one which showed Lyman alpha emission. So again, if Lyman alpha is really becoming that, it's getting, if the fraction of Lyman alpha escaping from galaxies at these redshifts is becoming that small, what you'd really like to do is push out to longer wavelength lines and try to detect light to give you a little confidence in what you're observing. So again, this requires more sensitive instruments, longer wavelengths, and much larger samples that you can collect with a reasonable pace with a larger telescope. So this again shows a simulation of what you would expect to be able to get with GMT in the same, and again, the same amount of time, comparing apples to apples with what you could get with the VLT today. And this is a simulation for a galaxy that is at a redshift of 8.5. And I believe this turned out to be a non-detection, but in any case. Okay, last point is the transient universe. Now remember I said we could have 7 instruments mounted simultaneously on the various instrument points, which would allow very rapid switching. In fact, the requirement is within 15 minutes in order to get onto a potential target of opportunity. So one question posed here is, can we use gamma ray burst afterglows to probe the ISM of young galaxies? And this is one of the reasons why gamma ray bursts in the transient universe are so interesting. It does allow us to probe galaxies, to probe the internal gas of galaxies that we otherwise can't even see. So the trick here is that while gamma ray bursts are easy to detect at their peak brightness at extremely high redshifts, they fade very, very rapidly. So the time scale here is showing 1 day out to here, and you can see the drops by many, many orders of magnitude. during that time scale. So the trick is to be able to get onto these sources within as rapidly as possible, hopefully within 15 minutes of their detection. And this shows the question, the original question I posed is, can we use gamma ray bursts to probe the internal gas of these galaxies? And the answer is obviously yes, it's been done. This is an example of that, where a gamma ray burst, this is probing not only the gas phase abundance of galaxies along the line of sight, but within the gamma ray burst host itself. And so this was taken with the Mike spectrograph on Magellan. And this is just, I don't want to go into these features in detail. I just want to illustrate how incredibly rich the information is when you're able to take a spectrum at such high resolution so rapidly after the burst is detected. And this shows a similar observation with the Subaru telescope and the FOCAS instrument. Okay, so that's just a lightning blur through some of the topics in the science case. The chapters in the science book are listed here, and I want to illustrate how those map to the instruments that have been chosen for first light and for the first generation of instruments, because these were very carefully considered. So for each of the chapters in the science book, what you see here is the degree to which they will be addressed by the instruments, by the first generation of instruments. So it's GMAX, which is the wide field instrument, NIRMOS, which is not planned for first generation right now, but I want to illustrate how important that near infrared capability is, so I'm leaving it up here. GCLEF, the high resolution optical, and to the near infrared high resolution spectrograph and integral field unit spectrographs, and finally the manifest with fibers. So green shows the science cases which are well addressed by those instruments. So you can see that our extragalactic science is really well served by the wide field optical spectrograph, by GMAX, and by a wide field near infrared spectrograph, multi-object spectrograph, and also by integral field units. Not surprisingly, that's consistent with the science cases that I was just covering. And the near the lower redshift science, stars, planetary systems, exoplanet systems, stellar populations, are generally better addressed by naturally the high resolution spectrograph in both the optical and the near infrared. There's some science case for the high redshift universe where we're talking about point sources, obviously, and this is not surprising. But I want to point out that GMT is currently the only ELT that's planned to come online with a high resolution spectrograph. So you can see very clearly here which science cases are going to be wide open for GMT and not addressed by the other ELTs. I just want to flash this up here and give you a little bit more detail on the instruments that are planned for the first generation, in case any of these are of particular interest to you, and you can get this talk from me if you want to look back at this, but I won't try to read through the table. And the last point I want to really illustrate about how we're planning to commission the telescope. So here we are in hopefully starting construction in 2014 and into 2015. The first stage of the construction will include the early procurements. We'll start out with trying to get the essential infrastructure on the mountaintop, the enclosure, the summit support building, the telescope mount critically that is needed to have support any mirrors whatsoever. And then we will try to come online with 4 of the primary and secondary mirrors. The next 3 mirrors will be required for, of course, to have the full aperture complete and to get to the diffraction limit. But we want to start commissioning as soon as we have those 4 primary and secondary mirrors available. I think this just first of all, it makes sense in terms of being the first on sky. It makes sense in terms of being able to start exercising the telescope, learning to operate the telescope. It just gives us the longest period of time to do commissioning, which is extremely valuable. And it lets us get to some of that first very early science that, as we learned from Keck, having an advantage in getting on sky with a large telescope is extremely valuable. So the plan is to come online with seeing limited science as early as possible, and then proceeding to a full aperture and finally diffraction limited observations and full adaptive optics towards the end of the commissioning phase. And that's where I'm going to end the talk. And if you'd like to see some of those videos, I'm happy to show them now, and I'm also happy to answer any questions. All right, we'll start one up.
For those in the background. So we have time for a few questions. Anybody like to start here?
What are the water vapor statistics for this site, and do you think it will ultimately be possible to work out at 20 microns with these telescopes?
20 microns is pretty far beyond, I think, what we're going to be able to do. But it's certainly true that this is a lower altitude site, and so the water vapor statistics are not quite as good as the higher altitude sites. But the details on that I don't know. They're available, I'm pretty sure, on our website. So you can get those in detail if you're interested. 20 microns, I think, is quite a bit farther than they'll be able to go.
It gets down in the wintertime. There are periods of pretty low water vapor. And
the 10 microns is...
It's about a millimeter of precipitable water vapor. It's
pretty good.
Reasonable fraction of the time.
For the AO system, which is the lowest wavelength that you can go? I saw 1.6 13 milliarc seconds resolution.
Right.
1.6 microns. How low can you go?
Right. So the question is the point at which the atmospheric coherence length prevents you from really getting good adaptive optics, and that happens around 700 nanometers. So in the
So you'll be able to do optical too in principle.
In the red, yeah. So, and certainly ground layer AO will be valuable at the red end of the optical range.
How are the observations going to work? Is it going to be Q mode, or is it going to be remote observing? Are people going to fly out, or a combination of all of the above?
A combination of all of the above is the short answer, but this is a question for the partnership to decide. This is not a question for the project office to dictate. But I think there's no question that if you want to really efficiently use a telescope like this, there needs to be some degree of Q mode. I think we'll also have, certainly also, I think the partnership, I anticipate, and at some level I hope that the partnership will demand to have more standard observer present observations for at least a fraction of the time. But the real question is what our Q mode will look like. So there are a wide variety of ways in which Q mode has been executed, and I think my own preference is that it be a highly human endeavor where it's more like service observing than anything else. But again, this is a question for the partnership to address.
And how about the funding for the telescope and the instruments? How you divide that? Which is the priority in that area?
Well, this was a frustration for me for a long time as the PI of one of the instruments for TMT. But now that I'm on the other side of the fence, I think it's perfectly reasonable that you really don't want to build the instruments until you actually know you have a telescope. On the other hand, you don't end up with any instruments. When you do have a telescope, if you don't fund the instrument projects, and I certainly feel this issue keenly, if you don't fund the instrument projects all along, they have to be sustained. They have to be, those projects need time to ramp up. If we want the instruments to be ready at first light, they don't just turn on like a faucet. They need time to ramp up. So it's a careful dance, but there needs to be some level of funding all the way through. And right now, the instrument funding is part of the core project funding. So it's right now about 120 million, the fraction.
So I guess last question.
You mentioned that you're at 85% of the partnership now. How contingent are the things in the next, say, 5 years on getting to 100%, or does 85% get you enough funding to at least assure that?
We'd like to get up to 100%. I think we're going to be adding there are a number of partners that we are in active discussions with, 4 that I can think of offhand, and there may be more. So I expect this issue to evolve fairly rapidly.
The 85% is aspiration, not cash in hand.
That's true. That's true too.
Charles, you had a
Okay,
question.
so I had a small technical question just to make sure I understood what you said. You need the central segment in order to be able to phase up the outer segments, is that correct?
Yes. So
you cannot really phase up without the center segment.
So this is actually a topic that's under some debate, but the current thinking about the current plan for phasing involves tying the segments together across 2 outer segments together across that middle segment. So you could end up with a piston inconsistency offset. Well, yeah, you could end up with uncertainty in what the correct piston solution was if you don't have the center segment.
Okay, well, sure, if you have other questions, Rebecca would be happy to have you come up afterwards. Thank her again.